So there's 2 data paths out of memory. That means there's 2 sets of ZEs for section 0. One goes to CPU 1, one goes to CPU 0. Same way with all the other sections. Okay, we've been talking about this memory for quite a while now. We talked about how many ports there are paths in and out, ways to send an address in and get data out, or ways to send an address and data in, if it was a write operation. We said that the scalar operation is something that's a little special. And the reason for that is because it's inefficient. We'll hold that off and give it the lowest priority. One thing we didn't talk about between CPUs is I/O has even a lower priority than anything else. So if you have an I/O reference waiting to do something in memory, he's going to wait until nobody else is using that particular section or bank before he can go. So he's going to say, well, if port A is not there, well, then I/O can go. And if port B is not there, then I/O can go, or C. Or if you're not doing a scalar reference, A or S register reference to any of those ports, then I/O can go. So you really don't have, I guess, the possibility of the conflict between scalar and I/O, because scalar is just a one-word transfer. You're only going to use one bank. If I/O can use the other 31, then, well, you're using that one. We talked about the parity, how we generate them. Look at the chart of x's. I think that's about it. We talked about all the different paths in or out. There's one thing we didn't talk about, however, and that is the memory timing. How long does it take to get something out of memory? Or how long does it take to complete a write? Now, I said that everything was fully segmented inside memory. So that means I'm going to give you the time it takes for one reference. You can have another one right behind that, and the only thing that it's going to take is the startup time extra. In other words, when I do a vector reference, I said I could do a 64-word reference, a 64-word read. It's going to take me X amount of time to get the first word back, whatever number that is, but after that I'm going to get 63 more words out of memory, one clock period right behind the other. And that's what makes this machine faster than a lot of the other ones, is that feature. All right, so this is how it works. That's address generation. It takes 2 clock periods for address generation in this memory. To generate an address, I mean all addresses are not a relative address, or are not absolute addresses. They may be relative to some other base address or limit or something. But anyway, to generate that address takes 2 clock periods. We then, since we have all these different paths or places to get an address from, it takes 1 clock period to select which address we want. So there's 1 clock period of address select. And now that we've got this address selected somewhere in the CPU, now we have to take this address and send it out to memory. And that takes 2 clock periods to fan out the address. Now we finally got the address onto the chips. All right, we already know how long that takes, don't we? How long is that going to take? 4 clock periods. Remember, once we hit that chip with an address, if we want to get anything out of that chip, we have to maintain that address for 4 clock periods and not change it, not allow it to change. If this were a write operation, we'd be finished, wouldn't we? Sometime during this address and selection and generation and fan out, we would have brought in our data also, and we'd be complete now. And it would have taken us, what, 2, 4, 8, 9 clock periods to do a write operation, roughly. If this were a read, it's going to take longer. Now we can get data out of the chips if it's a read operation. Two clock periods, data fan in. In other words, we got 32 banks out there. We got to decide which one of those 32 banks did we want to get the data out of. And so that takes 2 clock periods. Now we have to do our error correction. How long does that take? Does anybody remember? 2 clock periods, yeah. Two clock periods, we've got correct data now. Coming out of the ZEs, it takes one more, there's a line here, one more clock period. One more clock period to steer the data to which register is it supposed to go to now. So what do we got for a number here now? We got 2, 4, 8, 9, 10, 14 clock periods. 14 clock periods is the startup time of memory. All right. Every instruction in this machine takes 1 clock period to issue. At least. Some take a couple, take 2. But anyway, instruction issue time is 1 clock period. And I have to tack another clock period on the end over here because now that I've got this data steered to where it's supposed to go, it takes a clock period to latch it up in the register. So this time that I've just given you is for an A or an S register reference. And it's 16 clock periods. It takes 16 clock periods from the time I issue an A or an S register read until I get the data latched up in an A or S register. A block transfer is going to take slightly longer. The reason for that is we have more address generation and it takes longer to get the data into the register. So block transfer takes, let's see, 2 more clock periods of address generation and 2 clock periods. A block transfer takes 18 clock periods rather than 16. Is that right? Yeah. So that's the memory timing. 14 clock periods if you disregard this instruction issue and latch the data. So it takes 14 clock periods to go, send an address to memory, get data out, and get it ready to put somewhere. So do you have any questions about memory then? We've really completed then talking about this center section of the block diagram. We talked about memory, we talked about its address, its data length, how many ports in and out, how many data paths out, what type of error correction, and how long it takes.
This is the end of Section 1, Memory. Please stop the videotape and read through the key points for Section 1 in your course materials. After you've read through the key points, complete the exercises, check your answers, and then restart the tape player to begin Section 2. Section 2, Fetch.
Well, now that we've talked about memory, let's do something with it. We've got all these different things we can do with the memory data. I've been already talking about a lot of them. I talked about vectors and B and T's and A and S's. But first of all, let's go and do this one distinctive operation and load this instruction buffer. Well, we just talked about the memory timing. And we said it takes 14 clock periods, disregarding the issue and disregarding latching the data up, because everybody has to do that anyway. It takes 14 clock periods to get anything out of memory. If that anything that we want to get out of memory was an instruction, and if we just went and got one instruction at a time, it would take us 14 clock periods every time we went to get an instruction. As some of you already know, the instruction buffers here are 32 words. Since they are 32 words, if it took us the 14 clock periods every time we went to memory to get this 32 words, it would take us, what, 14 times 32, or a bunch of clocks, to fill an instruction buffer, wouldn't it? Well, they said there's a more easy way to do it. Just like we do a block transfer, we can go and we can reference memory, and it'll take us 14 clocks to get the first one, and 32 clocks to get the rest. Okay? Well, let's see, we're down to 46 clock periods now. That's pretty quick. But they said that's still not good enough. In fact, when Seymour designed the cray 1S, he says, I know a better way to do it. I've got 4 separate and distinct sections out there. I'll turn on all 4 of them at once. And on the cray 1S, his buffers were 16 words in length. He says, I'll get 4 words at a time out of memory, 1 from each section. It'll only take me 4 clocks to do it after the startup time. You still have the startup time no matter what. Well, when they were enhancing the cray 1S and making the XMP, they said, well, we have to use the same format. Now we still got our 4 sections, but we have twice as many banks, and our buffers are going to be twice as big. So we've got to speed it up somehow. Well, remember I told you there's 2 paths for data out of every section, aren't there? What they're going to do is they're going to say, well, we're doing a fetch, and while we're loading this, or while we're doing a fetch, which is this operation we're going to talk about, and while we're loading up this buffer, what we're going to do is we're going to borrow CPU 1's data path for a while. It'll still take us our 14 clock periods to startup time, but if we go and we borrow CPU 1's path and we activate all 4 of those separate sections at the same time, that means I can get 8 words out of memory at the same time. And then it'll only take me another, so it'll take me 14 clocks to get the first 8 words. It'll only take me another 3 clock periods to get the remaining 24, or whatever it is. Yeah, 24. So totally, instead of taking me 46 clock periods, it only took me, what? 17 and 3, or 14 and 3 is 17. And I'm done. That's a considerable savings in time. So that's what we're going to talk about, is this fetch operation, this distinctive operation where we go to memory and we turn it on and get 1 word out of every bank in memory in 4 clock periods, neglecting the startup time. So we're going to get 1 word out of every bank in memory in 4 clock periods. But if we're fetching this instruction out of memory and doing this fetch operation, first of all, we've got to know a little bit about what an instruction really is. We've got a data word here that's 64 bits in length, don't we? And here's our 64 bits, 2 to the 0 through 2 to the 63rd. Now there's a reason I divided them up like this, and that is an instruction in the XMP computer is usually just 1/4 of a data word. So that means since it's only 16 bits in length in one instruction, we can compact as many as 4 instructions in one data word. Now, since we've divided this up into little parts, this data word, we have to give it a name. So we're going to call them parcels. Each data word is made up of 4 parcels. Instruction parcels. So, as long as we're numbering here, we might as well number them. Now, I have to tell you that they numbered the parcels backwards because software got involved. Software's numbering system is backwards from the 2's format that hardware uses. So, parcel 0 is the upper 16 bits. 2 to the 48th through 2 to the 63. Parcel 1 then is the next 2 and 3. Parcel 3 is the least significant 16 bits. It's just the way it is. I don't know. Okay, so we've given them up to software and let them number our instruction parcels backwards. And now we've got our 4 instruction parcels laid out in our data word. Well, we've got 4 parcels in every word, and we've got 32 words in one buffer. How many instructions possible do we have then? 128, yeah. There's 128 instructions in each instruction buffer possible then. Now, if we look at if we take one of these instructions and look at it in more detail, I'm going to divide it up even farther into a G H all right, so our instruction, every parcel that we take, we're going to divide up into more separate and distinct little parts. We have a G, H, I, J, and K portion of an instruction. Now, there's no hard and fast rule here, but generally, the G and H portion of the instruction is the instruction decode. Generally, we're going to use the G and H portion of the instruction, which is the upper 7 bits of that instruction. We're going to use that, 7, right, 7, yeah, upper 7 bits. We're going to use that to tell us what type of operation we're going to do. If it were an add or a subtract or a multiply or a reciprocal or a whatever, a block transfer perhaps, we're going to use this upper G and H portion generally to tell us what type of instruction it is. If we have, for example, an add instruction in the operation code or instruction decode of the instruction, we have to have then some operands. If it was an add operation, we'd have to have some operands that we're going to add together. These are going to be register numbers. For example, if this was an A register add, the operation code, then we'd have to say we want to add A register 1 or the contents of A register 1 and maybe A register 2 together and put them somewhere. We have to put the answer somewhere, and so we have to have a result register. All right? This is the general format of an instruction. Now that doesn't follow 100%. There are some exceptions where they're going to use little different things to do it different. But anyway, this is the general format. About 90% of the instructions are of this format. We have an operation code, which is the G and H field of the instruction. We have operand registers, which are the J and K portion. And we have a result register defined as the K portion. For example, I said the G portion could be an add instruction. If it were, then we would have a G and H field that equaled this. The O30, the G and the H portion, which is a, Let me write it in red what it's going to decode out to here. There's our G field. And that is our H field. So we have an O30. That's O, or first 0 here, is a single bit all by itself. It's either a 1 or a 0. The O30 says A register add. If I'm going to add something together, I have to have some operands. I'm going to take A registers, the contents of A registers. In other words, I'm going to go and get whatever's in A register 2 and A register 3, and I'm going to add them together. And they can have any number. I'm going to add that number together, and I'm going to put the result of that add into A register 1. So, A2 contents plus A3 contents into A1. That's our general instruction format. The G field, G and H field is the instruction operation code, or the decode of the instruction. What does it do? It adds. The J and K are the operands. What are we going to add? The I field is where we're going to put the answer now that we did this add. Now, we can have as many as 4 of these instructions in every data word. We're going to execute one, well, I don't want to use that a little too harsh of a term. We're going to decode one of these instructions at a time and do whatever it told us to do. We're going to execute one of these instructions at a time. Every clock period, we could execute another instruction. Each instruction could do a separate and distinct operation. Well, before we can execute these instructions or go into the instructions in any more detail, first of all, we have to see where do we get these instructions from. And that is the fetch operation. We have to get them out of memory. Something loaded them up in memory, probably an I/O transfer. The I/O processor came in and gave us a bunch of memory from some user's program, loaded up memory somewhere, and then we started doing his program. First thing we have to do is we have to go to memory and we have to get these instructions out of memory and put them in an instruction buffer before we can do anything else. Now, I sketched up here on the board an instruction buffer. The instruction buffer is what we're going to load with this fetch operation. What we're going to do is we're going to go to memory, every section in memory, and we're going to turn on all 4 sections, and we're going to get 2 banks out of every section in 4 clock periods. Well, if you get 2 banks out of every section, there's 8 banks total in a section. In 4 clock periods, you'll have all 8 banks in each section, or all 32 words accessed. One of the things that we're going to do with this instruction buffer is we're going to define it hardware-wise that the only words that can exist in this buffer are words 0 through 37 octal or 40 through 77 octal. In other words, those are the only addresses that we can have inside this instruction buffer. We have to have word 0 here at the top, and we have to have word 37 in the bottom. Or it's, in other words, bank 0's data comes in and goes right into here in the first location in the buffer. And bank 32 decimal or 37 octal is going to be the last one here in the buffer. We're always going to fill the buffer in the same format, so we can't have uneven boundaries in there. You know, we couldn't have word 1 and through 30, well, what would that be? Word 1 through word 40 octal in there. Word 1 will be in a buffer, but it'll be in there along with 0 through 37. So the buffer boundaries are always 40 words, 40 octal words. So when we do a fetch, we're going to go, and we said we've divided memory up such that it's on 40 word boundaries all the time. We're going to get words 0 through 37, or 40 through 77, or 1030 40 through 1077 or any other 40-word boundary. But that's the only way we can do a fetch. When we go to bank 0 and turn it on, what we're going to do is we're going to activate bank n and n plus 4. Now something's going to define where we want to start our fetch operation. Just because we have to have the boundaries 0 through 37 doesn't mean that word 0 is going to come in first and 37 is going to be the last word. Remember, we're getting 8 words in at a time, aren't we? We're getting 2 words out of every section. Let's say, for example, that a programmer had a program that he wanted to start at location 0. Well, somewhere in this machine, since this has got to have a program in it, you have to have a program counter, don't you? The program counter in the XMP is called a P register. The P register is 22 bits in length, which is a memory address, plus a 2 to the minus 1 and 2 to the minus 2, which are parcel counters. All right, so here's our normal memory address. The P register can point to any memory address then, and in addition, he has 2 extra bits thrown on the end, so he can talk to either one of these 4 parcels. Totally then, the P register has got to be an address of 1 of 16 million parcels, doesn't it? And with 23 bits here, we can address 1 of 16 million parcels inside memory. It's just the normal 22-bit address with these 2 bits or parcel select bits appended onto the end of it. Let's see. Because when we start taking words out of this instruction buffer, we want to take out just one instruction at a time. And that's why we have the parcel select. And those are P register bits 2 to the minus 1 and 2 to the minus 2. They're the other side of 0, in other words. Any question on that? Now, the rest of our address here, the first 2 bits here of our normal address, 2 to the 0 and 2 to the 1, are our or our section select, aren't they? Do we really need section select as portion of the address to do a fetch operation? No, because I said we were going to go and we're going to turn on all 4 sections at once. So for this fetch operation, we really don't care what section we're activating because we're going to go to all 4 anyway. We do, however, care about the bank address portion. But when we go to memory, we're going to get banks n and n plus 4 all the time. For that reason, the only bits we're going to use then is which bank pair do you want to start at. In other words, we're going to get 2 banks out of every section. All we have to decode off of this P register then is which 2 banks do you want to start with. So when we go over here to activate section 0, we're going to get bank n and n plus 4. So we're going to get bank 0 and 4 out. If, remember, I told you this program started at 0, so our address here is going to be absolute bank 0 is the first word we want. We're going to get bank 0 and 4 out of section 0. At the very same time, we're getting bank 1 and 5 out of section 1. Bank 2 and 6 out of section 2, and bank 3 and 7 out of section 3. All 8 of those words are going to come into that instruction buffer at the same time. Since I happen to start up here, this is going to be the first group of 8 words that is going to come into the buffer. Why? Because I just happened to start at the lowest 2 banks there, didn't I? I said I want bank 0 first, and so it means the first 8-word group that I'm going to get in is going to contain word 0. That's the one that has the instruction that I want to execute. So here comes my first 8 words in. Now, the next clock period, the next address I want is banks 10 and 14 in section 0. So I say I want the next 2 banks here, 10 and 14, and along with that I want 11 and 15, and 12 and 16, and 13 and 17. Remember, they're 1 clock period behind the first 8. The next clock period after that, I'm going to go and get 20 through 20 and 24, 21, 25, 26, 22, 23, 27. Or the next group of 8 words. And then on the last fetch, there's 4 fetches altogether to make up this fetch operation, I'm going to get words 30 through 37. That's going to be our last group of 8 words. See, where's 17 end here? I think it's here. So when I did this fetch, I went and I got my first 8 words here. I brought them in all simultaneously into this instruction buffer the first clock. Well, it's actually 14 clock periods after I sent an address off to memory, isn't it? The next clock period, here's 10 through 17. Boom. 20 through 27. 30 through 37. Our instruction buffer is now full. We can now start taking these instructions off one at a time. We've got 200 octal instructions here, or 128 decimal instructions here that I can take off one at a time, execute those instructions, and do this program. Now, the only reason that I brought in the first 8 words here, 0 through 7, first, is because I said that's where the program started. What if the program didn't start at 0 through 7? What if the program wanted to start at 23? Let's see. All right, so here's my P register value, which is a 23-1. I'm going to use the dash to offset the parcel bits from the rest of it. I want this program to start at location 23-1. If I'm doing this fetch from ground 0, that means that somewhere, maybe I've got a subroutine back in the front of the program or instruction buffer here that I'm going to use a lot, and that's going to be 0 through 22 maybe. So I want my first instruction to be executed at 23.1 or dash 1. What I'm going to do now, I told you I didn't need these 2 bits for section because I'm turning on all the sections anyway. I'm going to take this bank address and say I want bank 4 out of all the sections first. Right? Well, if you go within section and bank 4 ends up being 0, 1, 2, 3, 4. 20 overall, doesn't it? So it says I'm going to activate bank 20 and 24. And I'm going to get banks 21, 25, 22, 26, and 23, 27 on our first fetch. So the first group of 8 words that's going to come in to that instruction buffer are going to be 20 through 27. The next clock period, I'm going to go to words 30 through 37. The clock period after that, I'm going to go back to bank 0 through and 4. Or I'm going to go backfill here and fill the rest of the buffer with 0 through 7 and 10 through 17. The reason for that, remember, is they have to be on 40-word boundaries. Well, if we've got this P register address and we're going to do a fetch, we have to send an address off to memory, don't we? What address are we going to have to send to memory? Well, you have to give memory an internal chip address. We have to give memory a chip select, don't we? But do we really need a bank select to send that to memory? Once we select a bank, as far as memory is concerned, all he's going to get is the upper portion of the address anyway, isn't it? He's just going to get 2 to the 5th through 2 to the 21st. The rest of it's going to be a control that says, up, bank, whatever, you're up. We don't need the parcel select to do a fetch operation, do we? We don't care. Memory doesn't know anything about parcels. All he knows is he's got 72 bits out here that he's going to send off to the ZE module when you do a read operation. We said we didn't need the section portion. We don't need the section portion because we're going to turn on all 4 sections at once. What about the bank portion of the address? Which bits are we going to need here? Of the next 2 bits up, 2 to the 2, 2 to the 3, 2 to the 4, what 2 bits are we going to need here to select one bank out of a possible 4 effectively now? 2 to the 2nd and 2 to the 3rd, right? We don't really need 2 to the 4th because 2 to the 4th we're always going to get bank 0 and 4 at the same time anyway, aren't we? So within this bank, wait a minute, that's not right. We need 2 to the 3rd and 2 to the 4th. 2 to the 2nd we don't need because we're always going to get banks 0 and 4. Right? 2 to the 3 and 2 to the 4 is what you need. Because if you look at this, remember, we don't care about these, so we can X these out. We can say, for right now anyway, we're going to go to all the sections. That means within the section, all we have is 0 through 8, or 0 through 7 banks. This bit we don't need because we're going to activate both 0 and 4 at the same time anyway. And if you put a 0 or a 4 in here as bank address, if you don't look at that bit, they're the same address, aren't they? And so what we do is we take these 2 bits, upper bits, 2 to the 3 and 2 to the 4, we send that off to memory, and we say section 0, section 1, section 2, and section 3. We want every bank address that starts with a 1, 0, and then you don't care about the last 3 bits. Well, what address starts with a 1, 0 and you don't care about the last 3 bits? Address of 20 fits into that description, doesn't it? How about 21, 22? Any address 20 through 27 falls into here, doesn't it? It says we want all the banks that start with a 2, and we don't care whether it's 20 or if it's 27, we want them all at the same time. See how that works? So we say we want bank 20 and 24. Those 2 happen to be in section 0. In section 1s, we want 21 and 25. In section 2, 22, 26. In section 3, 23, 27. We've got our group of 8 words now. We take that group of 8 words, put them in the instruction buffer. Now, we take this value, this was this P register value that the program gave us. This is where we wanted to start our fetch operation, at location 23-1, remember? The first group of 8 words now is going to contain this instruction, isn't it? We're going to take this value then and we're going to put it into a little 2-bit counter. This little 2-bit counter, we're going to start it at a value of 2 and we're just going to let it increment every clock for 4 clock periods. And we're going to use that as our bank select for our memory address. Remember the first one, we used this value. We said we want every bank that starts with 20. The next clock, we're going to increment this 2 to a 3 and say, okay, now we want every bank that starts with 30. Well, the next 8 words we're going to get are going to be banks 30 through 37. Now, if we take this 2-bit counter that we started at 2, we're going to get a 3. If we add one more to it, since it's only a 2-bit counter, what's it going to do? 0 out. It says, okay, now we want every bank that starts with 0. And that is 0 through 7, isn't it? Or 0, 0 through 0, 7. And then we're going to increment it one more time. And it says, okay, now we want every bank that starts with 10. And he says, okay, here's 10 through 17. And then this little counter says, hey, I've incremented 4 times, I'm finished. I can quit now. So what we're going to do when we do a fetch operation is we're going to take 2 to the 5th through 2 to the 21st. We're going to send that off to memory because that's our internal address and that's our chip select. We're going to take P register 2 to the 3 and 2 to the 4, which is our upper portion of our bank select, and we're going to put it into that little 2-bit counter. We're going to then send this command off to memory that says activate every bank 20 through 27 because we started at 20. And then next clock we're going to increment it to 3, and then we're going to say now we want every bank 30 through 37. And the next clock we increment it, and since it's a 2-bit counter it resets to 0, and he says, oh, now we want all bank zeros. And the next clock we're going to increment it one more time and say, okay, now we're going to bank 10 through 17, and we want all banks that start with 10. We're going to get them in, and we've completed our fetch operation. We've sent off enough addresses to memory. We've sent off 4 addresses. We said we want this internal address, we want this chip select, and we want all banks that start with 20, 30, 0, and 10. Okay, now we're finished. Now we have to wait our 14 clock periods. As soon as our 14 clock periods have transpired, what happens? Here comes our first group of 8 words, 20 through 27. It comes in here, boom, we write it in the instruction buffer. The next clock period, here's words 30 through 37. Write it in the instruction buffer. Next clock, all words 0 through 7, boom. Next, the last clock of the fetch, 10 through 17. All right. Any question on that, how we did it?
That's a total of 18 clock periods to fill the buffer.
14 for the first 8 words, 3 more,
So
17 clock periods, and we're done.
Now this is just one of the 4 possible buffers.
We're going to give this guy a name now. We're going to call him buffer 0. And when we fill buffer 0, is exactly what we do. If we start in the middle here, we're going to backfill and fill buffer 0. So buffer 0,
all the time.
buffer 0 is going to have all words 0 through 37. There's a reason for not starting at 0. Remember, the first word we want is right here. 20, 1, 2, 3, parcel 1. We want that instruction right there. If we start at 20 through 27, that means the first, after the first 14 clock periods, here's that instruction in the instruction buffer. The next clock, we can take that instruction off and move it off to that NIP register over there. At that same time that it's in NIP, the next group of 8 words is coming in. We can then advance that instruction to CIP. At that same time, the next 8 words, 0 through 7, is coming in. The next clock period, which is the same time the last group of 8 words is coming in, we can have that instruction ready to be issued. So we just saved 3 clock periods by doing it this way. And that's why. Every time you do a fetch, you save that, well, maybe save some time. And that's why they chose to do it that way. The hardware is such that once we fill a buffer now, before you can fill another buffer is you have to use all of the words in this buffer. In other words, you have to increment your P register to 37-3, at which time you're going to do another fetch operation and fill buffer 1 in this case. And then the next, as soon as you use all 200 of those instructions, then you'll fill buffer 2. And then as soon as you use them, then you'll fill buffer 3. And then if you had a routine that jumped back to 0, you'd have everything in the buffer and you wouldn't have to do any more fetches. Or if you had a routine that kept going, executing sequential instructions, you would then refill buffer 0 with new instructions. We also talked quite a bit about the control on this instruction buffer. We said the control is pretty simple. All we need is this P register. This P register, we're going to take 2 bits out of it to determine where we start our fetch. And those 2 bits can be any value, 0 through 3. And that's where we're going to start filling the buffer from. We're going to take the 2 to the 5th through 2 to the 21st, send that off as memory address for 4 clocks. Now, what else do we need? We need that 2-bit counter there. We need a memory delay timer, don't we? We'll say we know it takes 14 clock periods before we get our data back. So once we do this, we send off this for 4 clock periods. We go 1, 2, 3, 4. Okay. We've incremented that the same 1, 2, 3, 4. And now we sit here and say, well, we got some time to kill now. So we go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Actually, it counts an octal. At 14, it says, here comes the first group of 8 words. So he sends out a control signal that says to the instruction buffer, go fetch. And the instruction buffer says, oh, go fetch. All right, I know what to do. I'll write these 8 words in here. And now I'll increment my address and I'll write the next 8 words. And now I'll increment my address again and I'll write the next 8 words. And then I'll increment it one more time and I'll write the last 8 words. And now I'm done. All I had to have is a little counter that went 0, 1, 2, 3, and I'm done. No more words coming for this fetch operation. What am I using to send over here as a low address for the buffer? The program counter. The lower 5 bits of the program counter, aren't I? In fact, I don't even need all of that. All I need is a group counter. Group 0, 1, 2, and 3. Does that group of 8 words look familiar? That's the same count we used over there, isn't it? So we just take that same count that he used over on the other side for control. When he sends me the go fetch signal, I'll say, oh, we'll put them in group 2's place. Bang. We'll increment the counter, put the next group in group 3, increment the counter again, put it in group 0, increment it one more time, put it in group 1. I've incremented it 4 times, I'm finished. So we need 2 2-bit counters, 1 memory delay timer, and a P register. That's all we need for control. Well, not quite. There's one other thing we need to do, and that is we have to know when we need to do a fetch, don't we? Well, we said we knew we needed to do this fetch because we didn't have any other instructions in this machine, so we had to get some in. We did this fetch. Now that we've done it and completed it, we have to keep track of when we have to do the next fetch. The way we're going to do that is we're going to take 2 to the 5th through 2 to the 21st of the P register, and we're going to put it in something called an I-bar, which is an instruction buffer address register. And it's a 17-bit register. 17? Something like that. 17-bit register, yeah. And we're going to load this 17-bit register with 2 to the 21st through 2 to the 5th of the P register. So in other words, whatever this was equal to, we're going to stick in here. And we're going to have 4 of these instruction buffer address registers. We're going to have one for buffer 0, and we're going to have another for buffer 1, and another for buffer 2, and another for buffer 3. And we're going to compare this I bar 0 with the P register, 2 to the 5th through 2 to the 21st, every clock period. And if there's a bit-by-bit comparison or an exact compare every clock period after this, we know the instruction we want in buffer 0. Well, remember, we started out with a 23 here, didn't we? What did that look like again? All right, this is what we started out with, is a 23. The first bit here is 0, and every other bit is 0. So the value that we put in the I bar 0 was all zeros. Now, what are we going to do as we take this parcel 1 out and move it off to execution? We have to increment our P register, don't we? What are we going to increment? Which bit? We're going to increment, first of all, 2 to the minus 2 here, aren't we? And we're going to say, okay, we used parcel 1, now we want parcel 2. Then we're going to say, okay, parcel 2 is done, now we want 3, and increment on along. Eventually, what's going to happen? We're going to get our P register incremented to 37-1. Or 37-3, I'm sorry. And where's 37-3? It's the very last instruction in this instruction buffer, isn't it? It says as soon as we take this instruction off and move it to NIP, we've used every instruction in there, haven't we? Well, theoretically, maybe we didn't use the front ones, but anyway, as far as we're concerned, we need word 40 now, don't we? Because the P register incremented, if we increment this by add 1 to it, we're going to get a 1, 0, 0, 40, 40-0. Can everybody see that okay? We're going to get a 40-0. What did we do? We incremented this bit, didn't we? We no longer have an exact compare between I bar 0 and the P register. We no longer coincide between these two values, do we? The fact that we don't coincide or don't have coincidence between them, and we don't have coincidence with any of the other buffers because we haven't loaded anything, or any of the other I bars because we haven't loaded anything into any of the other buffers, says that we have to go and do another fetch. If we have to do another fetch, what are we going to use as our address? We're going to use the P register, which is equal to 40. And where are we going to get our first group of 8 words from? 0 through 7 is going to be our first group of 8 words. Remember, it's still these upper 2 bits that said 0 through 7. We're going to go and get the fetch. We're going to fill a buffer 1 with those 32 words, words 40 through 77 octal. And then we're going to take this value, 2 to the 5th through 2 to the 21st of the P register, and we're going to put that value into instruction buffer address register 1. And now as long as we have a bit-by-bit comparison between those two values, the upper bits of the P register and the I bar, we're going to not have to do a fetch until we lose that coincidence again. All right. What we're going to do now is what happens once we load the next buffer, and buffer 1 here, buffer 1 has got instructions 40 to 77. Buffer 0's got 30 through 37. What happens if somewhere in buffer 1 we have a branch that says modify the P register and make it equal to 10, parcel 2? Well, we change the P register here to 10, parcel 2. And now, remember, we're doing a bit-by-bit comparison between the I bar and the P register. Do we have a compare between the P register and the I bar number 1? What about the P register and I bar 0? We save that value when we load I bar 1, and we do a comparison against all of the I bars to see if we have a match. Since we have a match, it says, oh, the instruction we want is already loaded into buffer 0. There's no need to do another fetch, is there? So what we'll do is we'll just switch buffers. And we'll just go to buffer number 0 and start taking instructions out now. Now that's going to take a couple of clock periods to get that switch completed. In fact, it does take 2 clock periods. But once we switch, every time you switch buffers, there's a 2 clock period delay between one buffer to the next. Once we get that switch completed, though, we can now take off and start executing sequential instructions again. All right, now, there's also something called a 2-parcel instruction. And 2-parcel instruction is exactly as the word implies. We have an instruction that overlaps over 2 instruction parcels. Now, there's no limits on where that 2 instruction parcel, or where those 2 instruction parcels can be, other than they have to be right next to one another. They can be one at, where am I here, 23-3 and the last parcel at 24-0. They can wrap around word boundaries. They can also overlap buffer boundaries, which is the case Pam was talking about. What if the first instruction is here at, or the first half of a two-parcel instruction is here at 37-7, the other half is going to be then at 40-0. If 40-0 isn't already in a buffer, we'll have to go to memory and fetch it. So it'll be the 17 clock period delay between loading that instruction up into its instruction decode logic, the NIP, CIP stuff. As soon as that delay is complete, then we'll take the second parcel off, send it off to NIP, and then away we go. We're running again. If it already was in a buffer, all we have to do is switch buffers over. Once again, through the use of our I bars and our P register comparison. All right. Any questions on that? So we have 4 instruction buffers. We also have associated with those instruction buffers is 4 I bars, or 4 instruction buffer address registers, 1 for each buffer. Every time we do a fetch that fills one of those buffers, we take 2 to the 5th through 2 to the 21st to the P register and put it in its associated I bar register. That's how we keep track of what instructions are in what buffer. Every clock period we do a bit-by-bit comparison between 2 to the 5th through 2 to the 21st to the P register and the I bars, all 4 of them. If we have an exact match, we don't have to do a fetch. The only time we do a fetch is when we don't have an exact match. We don't have that no coincidence condition. We don't have that coincidence condition, I mean. Got one too many negatives in there. That's the control that says you have to do a fetch operation. The fact that you don't have an exact match between the P register and the I bars says go do a fetch. Once you do a fetch, we just turn over to the control logic, these little 2-bit counters. The P register portion goes off to memory. We have one more 2-bit counter, and that's which buffer to load. That which buffer to load counter is sitting there. It starts out as a 0, and it just increments every time you do a fetch. So the first fetch you do gets loaded into buffer 0, the next one goes into 1, the next one into 2, the next one into 3, and since it's only a 2-bit counter, once you get beyond 3, it increments back to 0 and keeps going, cycling through. 2-parcel instruction, which I didn't show you, I probably should have. The first half of the format is identical. We still have our G, H, I, J, and K on the first parcel, but the second parcel is called the M portion of the instruction. Let's see, right here. So our first parcel is our G, H, I, J, and K. And the next 16 bits of that instruction, of a 2-parcel instruction, is called the M field. The M field of an instruction is generally address or data. So in other words, if this instruction is a first parcel of a 2-parcel, what follows here in the M is generally part of the address, or maybe some data that's going somewhere. It's not really operand registers or anything like that. When we were talking about the fetch, we said we went to memory, and every section we got 2 words at a time out of, didn't we? Well, remember, way back at the start, I said what we're going to do is we're going to borrow CPU 1's path in addition to CPU 0's. Well, if CPU 0 here wants to do a fetch operation that's caused by the fact that he doesn't have the instruction he wants to issue in a buffer, he says, I have to do a fetch. I got to use memory, and I have to use all of memory for 4 clock periods, don't I? Well, what's the other CPU doing at that time? We can't guarantee that he's not using memory, can we? And we couldn't wait for him to stop using memory. And for all we know, maybe the last instruction that we issued before we needed to do this fetch was a vector block transfer. And we're using memory. In fact, maybe we issued 3 of them. And they're still going on. Well, we can't sit here and wait for memory to go quiet before we do this fetch operation then. What we have to do is we have to say, hey, we might want to take priority over everybody else here. So, when we get this no coincidence, this fact that we don't have this exact match between the P register and all the I bars, we say we're going to go to memory and we're going to tell memory to suspend all other operations. Just stop anything he's doing right now. That means we might have to wait for a bank conflict to subside, but eventually memory is going to go quiet. We go to the control of memory and we tell him don't send any more references to memory, either from CPU 0 or 1. So there's shared control there amongst memory. They say stop everybody right where they are. As soon as memory goes quiet then, as soon as the last reference that memory got off went away, then we go in here and we do our fetch. We're in there, we send our address, we get our 4 addresses off, we get our 32 words out, and then we can turn it back over and everybody takes up where they left off. It's easy to make memory go quiet. All you have to do is generate all the conflict signals and say, hey, you got a conflict. So every reference that's sitting there waiting to go has a conflict. And it's a fetch conflict, effectively. It says, just stay right where you are. You fired off, maybe you're halfway through a block transfer. That's fine. We'll finish. We'll get back to you. But right now, we got to do this fetch. So we can get some instructions down here to CPU 0. So CPU 1 does the same thing. Now, if CPU 1 is issuing some kind of a function unit instruction, that's fine. Those can take off and run. It's not until he gets to the memory instructions that he's got to wait and hold while we're doing this fetch. Okay? So when CPU 0 does a fetch, we borrow CPU 1's data paths out. Well, CPU 1 does a fetch, we're going to borrow CPU 0's. What if CPU 0 says, I have to do a fetch, but CPU 1's right in the middle of one? I said, well, we'll wait till 1's finished, and then we'll go. There's another case that can come up then. What if they both want to do it at the same time? What if they both get the no coincidence signal, both identically at the same clock period, and they both say, I want to do a fetch? It's a race to see who gets there first. CPU 0 always wins. This is a case that Dave was talking about. CPU 0 just says, the upper CPU says, you got priority, you go. The other one waits. So, what causes a fetch? No coincidence. What is coincidence? All right. All 4 of the I bars. You always compare all 4 of them. Now, there's another bit of the I bar that I didn't tell you about. And that bit is either upper or lower, but it's a valid bit. Only if that bit is set do we have to do that compare. So in other words, if that bit isn't set, when we first turn on this machine and dead start it, they're all cleared, it says none of them are valid, so there's no need to do a check. As soon as we fill one, then we set the valid bit and we say, okay, now this has valid instructions in it. And every time you load another one, we keep setting the valid bits. Maybe eventually they'll all be valid. Now, if we bring a different program in here somehow, whatever means we use to swap programs around in this machine, when we do bring that new program in, we'll clear all those valid bits again and say, yep, the instruction buffers are no longer valid. Why? They're somebody else's instructions. And generally, programmers don't want to execute somebody else's instructions. All right? The control for the fetch operation. We need the upper 17 bits of address to send off to memory to get our internal chip select and our internal chip and our chip select. When we do a fetch, we're only talking to one chip, one internal address at a time, aren't we? We're going to one internal address inside one chip when we do a fetch and getting that word out along with all the other words in there in all the other banks, getting one word out of each bank and put it in the buffer. We use 2 to the 3 and 2 to the 4th of the P register of the address to determine which bank's pairs to get first. And we go and we get bank pairs n and n plus 4. That's what that equals to. Works out to be n and n plus 4. You say, I don't know what it is, but I know there's an n plus 4 that goes with it. It's 0 and 4, 1 and 5, etc. 20, 24, 30, 34. We get a group of 8 words. We get the group of 8 words, we load them in the buffer using the same information, that same P register bits, as our starting group location. So we use P register 2 to the 3 and 2 to the 4. That tells us where to put the data, which portion of the buffer to load first. We then load it up. We use that same little 2-bit counter type deal to increment it from 2 to 3 to 0 to 1. And we circularly fill the buffer. Now we've got one more 2-bit counter that tells us which buffer to load. We do a fetch, we load up buffer 0. As soon as we finish that fetch and load up I-bar 0 and set the I-bar valid bit, we increment our buffer pointer from a 0 to a 1. So there's another little 2-bit counter here that says and if it was set to a 0, as soon as we load buffer 0, we increment it to a 1. And we say, next time we do a fetch, we're going to put it in buffer 1. Once we do fill buffer 1, we're going to come in here as soon as it gets filled, and we're going to increment it again and say, next time we do a fetch, we'll load buffer 2. All right, once again, another 2-bit counter. All right, any questions on the fetch operation? Well, we've talked about how we load this buffer, how we do the fetch operation. All right, well, we've got it loaded now. Now let's take some data out and get some instructions out here and do something with them. Once again, we're going to use the same P register. Our P register is 2 to the minus 2 through 2 to the 21st. Remember, we've got our parcel bits here. We'll put our 23-1 out there again. What we're going to do now, remember this first group of 8 words that came in here contained the instruction that the P register is pointing to, which is 23 parcel 1. As soon as those 8 words come in here, in fact, along with those 8 words coming in here, what we're going to do is we're going to take all of word 23 here, and as soon as it gets here, we're going to put it right into a readout register. Let me move this up. So we're going to fill this buffer readout register with word 23. Now remember, we wanted just parcel 1 of word 23. Then what we're going to do is we're going to take the parcel bits, or the parcel bits are going to be presented to this register called NIP. Those 2 bits of the P register, 2 to the minus 1 and 2 to the minus 2, come in here to the NIP register, and he says, I know now that I have to take out of here parcel 1 and load it into here. All right? So he is presented with the whole word 23, and he decides which one of 4 parcels he wants. That makes the instruction buffer's job easier. All he has to do is say, I know you want word 23. I'll let you decide which parcel you want. All right? You see how that works? So he says, I don't have to decide which parcel to put in the readout register. I'll just put the whole word, and you can take your pick. All right. Now, right away, everybody starts to see there's some problems here. If I take out parcel 1 here, eventually I'm going to get down here to take parcel 3, and then I want you to switch words. And won't that take a while to switch words? Well, it would, but we have a built-in look-ahead circuit on this readout register. So this readout register says, when I put up here word 23, as soon as you take parcel 1, of word 23, I'm going to increment from 23 parcel 1 to 24 parcel 1. Because I know you aren't going to back up and want 23 parcel 1 again. Once you get it into the NIP register, there's no way you can put it back in here. I'm going to then keep advancing this I'm going to keep advancing this parcel 1. I'm going to move it and advance it to CIP. I'm going to then have 23-2 in NIP. And since I've taken 23-2 off of here, he says there's no need to keep 23-2 here any longer. I'll go and I'll increment to 24-2. Well, it also tells you he probably, at the same time he loaded this in, loaded up 24-0, didn't he? To stay ahead. He says, okay, now the P register at this time is pointing to what word? Or what parcel? Remember, every time we take an instruction out of here, we're going to increment this, aren't we? So he's sitting there at 23-3. He says, that's the next one to come out. You've got 22-2 here. You're going to, at some point in time, advance everything ahead here. And what happens? I'm going to increment to 24-0 then, aren't I? As soon as I load up 23-3 into NIP, that increments to the next one. All right? The same time you load it, it increments to the next. And this guy can go ahead and get 24-3 and put that in the readout. And that's how we stay ahead of this swapping word boundaries. As soon as you take out a parcel from one word, he says, as soon as you take 24-0 off of here, I know you never want to use 24-0 again. And all I'll do is I'll put 25-0 there, because generally we just sequentially go through instructions. He says if you do a branch operation where we modify this P register, I might have to do a fetch anyway. Or I might have to switch buffers. In any case, I'll have plenty of time to go back and refill this readout register. All right? So we have what's called a parcel look-ahead on this readout register. We just stay a word ahead. I guess a word look-ahead rather than a parcel. We stay a word ahead on the readout register all the time so that whatever parcel you want, whatever word you want, it's there as long as they're sequential. If it's not sequential, it's some kind of dynamic operation where you're doing a fetch or a branch or something like that anyway. Look-ahead comes into play even on the first load.
Okay, so
He said, since you wanted 23-1 here, what I'm going to do is this. I'm going to put 23-1, 23-2, 23-3, but I'm going to put 24-0 because I know you aren't going to go back up.
He just senses.
So he looks ahead right away as soon on the first load, exactly. All right. What controls this word look ahead is called a past pointer. Well, maybe I could write that out. Past pointer. Yeah, past pointers. And he says, I have a past pointer. Maybe I make, instead of pass, I'll make that past. Because that's what it is really, past pointer. He says that past pointer for 0 says, when you're loading this up, your P register is already past parcel 0, isn't it? And so I'll get this past pointer 0, which will increment my word address by 1. Then when I take 23-1 out, I'll get past pointer 1 that says you're past parcel 1. You've incremented to 2. I'll put 24-1 in here as soon as I get that. I'll get a past pointer 2 when I take 23-2 out, and I'll increment to 24-2. I don't get a past pointer for parcel 3 because my word address is going to increment on its own, isn't it? He says, as soon as you take 23 out, I know my word address switched to 24 anyway, and I'm working, remember, this is a word readout register. So I'll just let this guy take care of 24 or parcel 3 by himself. He's got 3 clock periods, a minimum of 2 clock periods if it was a 2 parcel instruction to get it loaded anyway, which is plenty of time. All right, any questions on the readout then? Remember, what controls the readout is the P register. Actually, remember I told you just the upper bits here are going over to the instruction buffer. He doesn't even know about the parcel address other than to get a pass pointer whenever you're past that particular parcel. So the word address is what we're controlling here. He says if I've got a buffer readout register, I'm going to put a whole word in it unless you send me a pass pointer that will increment the word address for that particular parcel. All right, everybody understand that? I don't know how I could have said it that way, but it sounded good to me. NIP is our next instruction parcel. CIP is the current instruction parcel. There's no more questions about the fetch operation or the reading out of the data out of the buffer. We'll go on and we'll talk about the issue operation here. Instruction issue. We've just did the fetch. We've loaded up the readout register. Remember, our first 8 words just hit here. At the same time the first 8 words hit here, the buffer readout is loaded. Exactly like this, with 24-0, 23-1, 23-2, and 23-3. The next clock period, we take this data out of the readout. Let's see, if I do this right. There. And we load NIP. As soon as we load NIP with instruction 23-1, our P register increments to 23-2. It's a next clock period then. Let me put this in here too. There's another box here called the lower instruction parcel. All right. Assuming that the first group of instructions here are all 1 parcel instructions, we're going to advance this 23-1 here. In NIP is going to be 23-2. At the same time that hits that NIP register, our next instruction parcel, we're going to increment this to 3, 23-3. Now, this instruction is now in CIP. At this time, we have to make a decision whether this instruction can leave CIP or not. Now, there's several things that come into play here before we can make this decision. The first thing we have to decide is, what kind of instruction is this? In other words, we have to decode the instruction. We look at that opcode, the G and H portion of the instruction, and we say, what is this? What does this instruction want to do? After we decide what kind of instruction is this, then we say, can this instruction run to completion if it leaves CIP? In other words, are all the resources that this instruction needs to do its thing available? Well, if this is an add instruction, an address add, let's call it that for now. If it's an address add instruction, what do we need? We need the operand registers. They have to be available. In other words, nobody else can be using them right now. And we need a result register, don't we? Now, because of the full segmentation built into all the functional units, we don't have to worry about the address adder, because if anybody was using the address adder ahead of us, by the time we get there, there'll be a set of latches available for us to load. So we don't have to check to see if he's available, because we know it's available. By the time we use it, it'll be available, even if it's being used now. So for an address add, we check registers. And we check those registers to see if they're reserved. Reservations. If they're reserved, that means somebody else was using them as a destination register and the data hasn't got there yet. Everybody follow that? We're using them as if they're reserved, if there's a reservation on them, that means that some other operation was using them as a result register and the data hasn't got there yet for that result. In that case, this instruction will stay in CIP. All right? What that means is there's a recirculation path on here. If it can't leave CIP, it recirculates and comes back in. It actually does that. It's a set of latches that actually refill themselves again. Well, if CIP is recirculated, that means NIP better recirculate also, huh? And it's exactly right. Let's see now. That has a recirculation path also, NIP. And if NIP can't move its instruction parcel out of NIP to CIP, that means the P register can't increment. So guess what? He does the same thing. He also has a recirculation path, which is the non+1 path. I should have went the other way. So they just refill with the same value again, dependent upon whether this instruction could leave or not. As soon as this control module, CIP module, determines that this instruction can leave and run to completion, he lets it issue. And he lets it go out here to execution. As soon as an instruction leaves the CIP, we call that clock period 1 of an instruction. Remember, everything's fully segmented, so every clock period we can predict from CIP on out how long that instruction is going to take. Remember, we also determined that everything's available for that instruction before it left. So we know it can't stop and wait because there's nothing to wait for. That's the supposition that this machine is built on. All of the instructions, once they leave CIP, are going to run to completion. Now, there's a few minor exceptions, but we'll talk about those. So before we'll let an instruction leave CIP, we make sure that it can run to completion. That way we don't have to hold anything up once it leaves. Once it leaves, it's gone and it'll finish. We don't have to check on it anymore. We know it'll finish. If it's an add, it'll do the add. It'll have the operands or data. Operands will come into the adder. They'll come out of the adder. The result will load up to the destination register or result register. At some point in time, it'll be done. We don't have to go and check on it. We know it'll finish and exactly how long it'll take. All right. Whew. Any questions on that so far? I haven't talked about LIP yet, but I will here shortly. What we've got here is a little pre-decode logic here. We've got a little box here that's pre-decode. And what he's doing is he's looking at the instruction as it comes out of the buffer and determining whether it's a 2-parcel or not. He says if this is a 2-parcel instruction, what I'm going to do is I'm going to move this arrow over and control this instead. What I'm going to do is I'm going to open this little switch here. So in other words, as soon as I identify that there's a 2-parcel instruction coming, the first parcel of a 2-parcel is going to be here. Oops, I didn't spell that right. Okay? So we're going to load the first parcel into NIP. At that time, we're going to break this switch. And remember how I had it drawn before? Well, let me go back here. At the same time that the first parcel's in here, the first parcel's already also down here. Because those are at the same time. So when I load this instruction, the first parcel of a 2-parcel in here, I put it in NIP and LIP. All right? Now, I've decoded it and I said, oh, this is a 2-parcel instruction. Now break this switch. Now when this instruction, the first parcel of a 2-parcel advances to CIP, at the same time, the second parcel is going to come down in here. All right. At the same time I advanced from NIP to CIP, I load up LIP with the second parcel. All right. At that same time, there's nothing coming into NIP, so he's blank. All right. Now, if this is a 2-parcel instruction, it's going to do some type of operation, and it needs that second parcel to issue both at the same time, or issue along with the first. So when this instruction, the determination has been made that this instruction can go and execute or issue, we're going to move the first and the second parcel out to clock period 1 at the same time. All right. At the same time that we've determined we can issue that, this switch goes back to this condition. The blank moves ahead to CIP. And we've got a new instruction in here and down here. All right. Now, the next clock period of this instruction, whatever it is, clock period 2, it's going to be here. It's going to be out there doing its thing. Well, what's in clock period 1 at that time then? Nothing, yeah, the blank. Our new instructions and then CIP and NIP's got something in it. New plus 1. Any question on that? So every time you load NIP, you're also loading LIP with the same value. The only time you aren't is when NIP says, oh, that's a 2-parcel instruction. As soon as NIP says that's a 2-parcel, that switch opens. The second parcel is going to come down here to LIP. The first parcel advances to CIP. So LIP is really the same time as CIP, isn't it? But it also gets loaded at the same time NIP is. The 2 parcels then issue together. Remember, on a 2 parcels, the second parcel is data or address, so you have to have that right away. They're going to go out to clock period 1 together. The next clock period, there's going to be a blank instruction, or nothing there. Now, in the hardware reference manual, it says a 1 parcel instruction takes 1 clock period to issue. It also says on every 2 parcel instruction that it takes 2 clock periods to issue. Well, the 2 clock periods are the time it takes to get that blank out of CIP and get a new valid instruction in there. So that's our 2 clock periods. Any questions on this? That's the instruction issue. The basic thing about the instruction issue in the XMP is generally an instruction will not leave CIP until we know it can run to completion. So it's going to sit there in CIP until everything is available that it needs, and then it will leave. Now, there are some exceptions to that. The exceptions are memory type references, because we don't know about bank conflicts yet and stuff like that. But everything other than something tied up with memory is going to run to completion when it leaves CIP and not get interrupted. I'm going to talk about instruction issue in a little more detail yet, but it's hard to talk about the instruction issue before you know, or without using any instructions. And before you can use an instruction, you really have to know what the registers are like, so you have an idea of what you're working with here. So I'm going to talk in some more generalities about the instructions before they issue, at which time then we'll go and we'll talk about the registers, and then we'll come back and really hit this instruction flow a little harder with actual instructions. What we'll try to do is we'll try to look at 1 or 2 types of every instruction. We won't look at all of the instructions, but we'll look at all the different types and how long it takes them to get through to clock period 1, and then how long it's going to take from clock period 1 out to execution. We'll even time out some instructions totally. But any questions on the stuff that we talked about this morning at all? All right. Well, let's put an instruction type into CIP here and talk about it a little bit. One of the things we already talked about an example and I'm going to group these instructions by register types. So an A register instruction, we said that, for example, an A register add, what we had to check while this instruction is in CIP is we have to check and see if the resources are available. For an A register type instruction, those resources are the A registers. Are any of the A registers reserved? Remember, when an instruction that uses the A registers moves to clock period 1, at that time he will set a reservation on any register that he needs to reserve, or any result register. And once again, we used add as an example. Now, we'll talk about this in more detail after I've explained a little bit about the A registers, but for right now, for an A register type instruction, all you have to check is register reservations. That's it. All right, any question on that? Why don't we have to check the functional unit reservations? Because of the full segmentation. When we're talking about A registers, and actually this also applies to A and S registers. An A or an S register type instruction, it's only one operation we're talking about. We're doing an add, or we're doing a shift, or we're doing a logical, or we're doing a multiply. But it's only one set of operands, and we're getting back one result every time we issue one instruction. For that reason, all we have to worry about is the destination register. We have to make sure that nobody uses the destination register before the data gets there, which makes sense. You don't want somebody taking the data out of a register before the new data has gotten there. And that's all we have to worry about. There are no functional unit reservations or anything like that. Okay. Now, leaving these A and S register instructions grouped together, what I talked about are the functional unit instructions, the ones that do an operation, an add, a multiply, a subtract, a reciprocal, or whatever. Whatever you can do with 2 A registers or 1 A register and S register, all you have to worry about is the destination register reservations. Any question on that? What if this is an A register memory instruction, however? And once again, it applies to both A and S register instructions. When this instruction is in CIP, what do we have to check for? Let's say it's a memory read. We're going to read someplace in memory and put the data in an A register. What's one thing we have to check for, first of all? That's two things. All right. The first thing is we'll have to check, somebody said, the register to make sure the register is available. If we're going to load, let's say it's 2A4, and there's a register called A4. If we're loading A4 with memory data, we have to make sure and check to see if A4 is reserved. If it's reserved by some other operation previous to this, we won't be able to use it and load the data in until they're done with it. So we have to check A4 reservation. Somebody else said the memory ports. Which port do we have to check? Port C. Any other port? We're doing a memory read to an A register, A4.
So it'd be A because B uses A.
Uh-huh. Anything else? Remember, this is an A or an S register transfer. And I said one of the things that you do on an A or S register transfer is make sure ports A, B, and C are all available. So it's port A or B or C reserved. Now what I've got up here are the questions that you have to make sure you have to answer before you can issue this instruction. In other words, if A or B or C is reserved, this instruction will stay in CIP until that condition goes away. All right? If A4 is reserved, we'll wait in CIP until that A4 is no longer reserved, and then we will issue. All right? Any question on that? So, port A or B or C reserved will stop this instruction in CIP and it will wait. All right. Now, once we have these conditions met, and those are all the conditions we have to meet, we're going to let this instruction go to clock period 1. Once again, this is A or S. Register, memory read. When that instruction advances through issue here and gets to clock period 1, what are we going to reserve now? Right, we're going to reserve A4. Why do we have to reserve A4? It's going to take what? 14 clock periods for the data to get there. We don't want anybody taking that data out of A4 and expecting it to be our memory data until the memory data is there. Exactly. Anything else? Reserve. What we're going to do is we're going to reserve the ports. Well, wait a minute. That's not really a reservation in this case. It's not like a port reservation would be for a block transfer. What we do is we just stop any block transfers. For 3 clock periods, we don't allow any instructions if there's, in other words, if a block transfer hits CIP and there's a or S memory read in clock period 1, we're going to wait here for 3 clock periods before we'll issue. So we stop any block transfers for 3 clock periods. So if I advance this another clock, A4 is still reserved. Memory read to A4 and at clock period 2, we're going to stop any block transfers for 2 more clock periods. So it's just a little counter somewhere that says, oh, you can't issue one for 3 clocks, now 2, now 1. Okay, now it's all right to issue. All right. Now, what did we say the reason for that was? Well, we get our A&S reference out the door, but we also don't have to worry about a block transfer leaving CIP and having a bank conflict right away. That's a special case type instruction. Once again, it's going to run to completion now. And A4 is going to be reserved for our 14 clock periods, or thereabouts. Until the data gets there, and until it's so close that by the time you issue an instruction, if you wanted to use it, he'd get the right stuff anyway. Understand it might take, some time to get the data out of an A register or something. Any questions on that? So we talked about A&S register type instructions. If it's a functional unit type instruction, all you got to worry about is a reservation on the registers. If it's a memory reference instruction, we got to worry about all the ports being available and the destination register being available, or result register if it's a memory write. If I change this to a memory write instead of a read, the only difference is, well, there is no difference. Except that when we issue, we won't reserve the register, because there's no need to reserve an operand register because we've used it already. It's on its way to memory. If, let's say, something's broke in the machine and A4 is always reserved, when this instruction hits CIP, what he's going to do is wait until A4 is free. And if A4 never comes free, he waits until A4 is free. He just sits there and waits, and the machine won't do anything until A4 is cleared. The reservation's cleared. Now remember, this is something broke, so that's one of the conditions that could happen to a machine. You lock up a register reservation and keep it all the time for some latch that's broke or something like that. An instruction that wants to use that register will hit CIP and it'll sit there and nothing else will happen until you come in and do a master clear. Now, what about another one of these instructions? Could I issue another one of those? A or S register memory read, as long as it's to a different A register. Because I didn't reserve the ports here, that's why I had to skip around that. Because I didn't reserve the ports, it's okay to issue another one right after that. So you could keep issuing A or S register reads or writes. As long as you don't run out of registers, you can keep doing it. Now you might have some problems if you run into bank conflicts. Things will start to back up on you, but we'll talk about that later. Any questions on A or S register type instructions then? All right, I'm going to put a vector type instruction in here then. Now, this vector instruction, if it uses a functional unit, what's one thing we have to check for then? If it's going to use a functional unit or anything else, it's going to have operand and destination registers, right? So we have to check the register reservations. If any of the registers that we want to use for this operation, let's say it's a vector add, we're going to add two vector registers together and get a result. What we have to do is make sure that none of those three registers are already being used by a different operation. If they are, we'll hold issue. We'll stay in CIP and wait for it to clear. We'll hold the issue of that instruction. Now, vector registers are kind of special. When you do a vector operation with one instruction, you can do as many as 64 distinct operations. Because of the way they're built, if you issue a add vector register 2 and 3 and put it in 1, you could get 64 different answers back. In other words, you take 64 sets of operands, you send them off to the adder, and you get 64 results back. For that reason, we run up against a functional unit reservation. If we're going to be using a functional unit for 64 clocks, we have to reserve it. Remember, we said they're fully segmented. We can send a set of operands every clock. In A&S registers, all we can do is send one set of operands. But with the vectors, we could send up to 64 operands. For that reason, we have to reserve it for the length of the vector operation. So, if it can be reserved, then we have to make sure it's not reserved before we issue. Check functional unit reservations. Any question on that? Go ahead.
So shouldn't we have checked the functional unit reservation on the A or S ad?
No, because they're fully segmented, and with an A or an S add, all you can do is one set of operands that can get set.
What if you started your vector ad and you're going through 64, but you've only done 36 of them?
There's three separate adders,
Oh, okay.
so we don't have that problem. Okay. Like I say, there's a, well, it's hard to talk about this stuff until you know something about the registers, but I'm trying to get some of the generalities out, but that's one of the things that will come out. Okay, so for that reason, we don't have to worry about it. But the functional units have to be reserved when we issue then also, don't they? So when we go to clock period 1, we're going to reserve. Now in A and S registers, all we reserved was the destination register, wasn't it? Well here, because we're taking more than one element out of this register, we have to reserve all three of the registers involved. So reserve both operands and destination. Destination? I don't know. Anyway. I guess. So we have to reserve both destination and operand registers. Operand and result. I know how to spell result. Put that up there. And reserve the functional unit when it issues. Okay. So vector register type instructions are different. A vector register instruction, you have a possibility of conflicts on 3 registers rather than just one. When the instruction issues to clock period 1, then, you're going to have to reserve all of the registers involved in the operation. You're also going to have to reserve the functional unit. What about a vector memory operation? Vector read. If we're doing a vector read, what do we have? What's one thing we have to check to see if it's reserved? The port. Which port? Port A and B reserved. If just port A was reserved, we could use port B. And likewise, if just port B was reserved, we could use port A. But the only thing that will hold this in CIP is if both of them are reserved. We also have to have destination register. The register reservation also. Any question on that? We have to make sure nobody else is using the register that we want to use. Okay? When this instruction issues, then, what are we going to reserve? If both of them are free, which one are we going to use first? Port B or A reserved. So I wrote them. B first and then A. First and second choice. What else? Destination register. Okay. That's the basic issue philosophy of the XMP. Vector operations, you have to reserve the functional units and all of the registers involved in the operation. And since you reserve them all on the way out of CIP, when you get in CIP, you have to make sure they weren't already reserved. Now remember, the hardware is going to handle all this. This is the things that the hardware does. Now, we'll continue discussion of the issue philosophy as soon as we learn some more about the registers.
This is the end of Section 2, Fetch. Please stop the videotape and read through the key points for Section 2 in your course materials. After you've read through the key points, complete the exercises, check your answers, and then restart the tape player to begin Section 3. Section 3, A and S registers.
All right. Now we're going to move up the block diagram and we're going to talk about the A registers. The A registers are 8 in number, A0 through 7. Works out kind of handy. We've only got 3 binary bits that we can use to point to one of them in the I, J, or K field of the instruction. So we can't have any more than 8. They are 24 bits in length. They're 24 bits in length. Associated with the 24-bit A registers are some B registers. The B registers are also 24 bits in length. There are 64 B registers. They can be block loaded from memory. In other words, you can go to memory and you can read up to 64 memory locations and take those memory locations out and put them in 64 B registers. Only the lower 24 bits of the memory location gets transferred into the B registers. It's a non-destructive read, so what was ever above there, the upper 40 bits, is still there in memory somewhere along with the other 24. But you only get the least significant 24 bits transferred. You can transfer a B register to an A register. There's a 1 clock period instruction. In other words, it costs you 1 clock period to transfer a B register to an A register. The B registers then are a buffer for the A registers. You've got a big 64-word buffer that you can fill from memory. It costs you 1 instruction to load that up from memory. And now you can, with 1 clock period instructions, transfer information between B's and A's. That's much quicker than taking an A register and writing it into memory or going and reading an A register from memory. Or reading memory and putting it in an A register every time. Every time you go to memory, it's that 14 clocks you burn up. Here you can fill all 64 in, well, I said it was 18 clocks plus 16 clocks plus 63, so that it takes longer for a block transfer to B registers, 2 clock by 2. But anyway, you only have the startup time of 1 and then the block length. Whereas with A registers, to go and get 64 A registers is 64 times 14 clock periods, considerably more. So you can use the B registers for a buffer. The A registers have associated with them their own functional units. There's an A register adder, an address functional unit. It takes 2 24-bit operands, adds them together, gives you a 24-bit result. No overflow detected. No carry. Nothing. Take 24 ones in, you get 24 ones out. That's it. It also has a multiply functional unit. You can take and multiply 2 24-bit operands together. Once again, you get a 24-bit result. The least 24 bits, the least significant 24 bits. So if you really want to do a multiply and get accuracy, you want to keep your numbers down around 12 bits or less. Otherwise, you're going to end up losing the most significant portion of the answer. Okay? Any question on that? Now, the address registers can also go and get transferred to other locations. In other words, it shows here an A register going into a vector length register, whatever that is. And it comes back from a vector length register back into an A register. It also shows one going to an XA register. It also shows AI and AK being used for some of the other functional units on the block diagram. You can also transfer between A registers and memory. You are capable of doing that. The B registers. When you load the B registers from memory, you can also wrap around. In other words, you can start at any B register and load it from memory, or the other way. Also, you can write any one to memory. But you can start at any B register and it will wrap around and do the rest of them. For example, if you wanted to do 64 B registers and if you wanted to start at 40, you go to memory and get your first word out of memory and put it in B register 40, and then the rest of them would circularly fill the B registers. And so your last word that you transferred out of memory would be in location 30 or B register 37. Okay, so they circular fill. And you can load any part or all of them. You don't have to load them all. You can transfer one B register from memory, although it doesn't hardly pay, but because it takes two clock periods longer to transfer it to B register than it would have to transfer it to an A register anyway. And you still have to get it from the B to the A, but you can do it if you want to. All right. Any questions about those then? That's the basic information behind the A registers. 24 bits in length, there's 8 of them. B registers, also 24 bits in length, but there's 64 of them. They can be circularly filled. I don't know if that's a word or not, but it is now. All right, now that we know something about the A registers, let's look at a specific instruction for the A registers. If you open your hardware reference manual to page 5-34, yes, 5-34, you'll see the O30 instruction. I've taken an O30 instruction and I've filled in the I, J, and K of the fields of the instruction. Remember, the G and H portion is the O30. That's the operation code. The CIP register, when he gets this O30 in there, he strips off the O30 part and he says, this is an address add. I'd better check for, it's an address register instruction, so I have to check to see if there's any reservations on any of these address registers. And he says, which address registers? Well, the I, J, and the K field of the instruction. So we check reservations on A1, A2, and A3. What about the functional unit, the address adder? That little box over there in the block diagram. Do we have to check him? No, he's fully segmented. He can handle as many address instructions like this, one right after another, as you can do, until you start running into reservation problems. So, this instruction is in CIP. What if A1, 2, or 3 is reserved? What's going to happen? You're going to hold issue. What happens to CIP? It gets recycled or recirculated. Right, exactly. Well, let's say that this instruction was the first one out of a buffer, so there's not possibly anything that can go wrong here. This instruction is going to be here for one clock period in CIP, and then it's going to issue. It goes to the very first clock period of an O30 instruction. What are we going to reserve at this clock period 1 of this instruction? A1. Well, if we're going to do an address add, we'd better get this data out of A2 and A3 and send it on its way, right? Because what we're going to do is we're going to take A2, the contents, plus A3, the contents, and put it in A1. We're going to take those two 24-bit operands, we know how big they are now, We're going to send them off to that address adder, and they're going to get added together and give us a 24-bit result back in A1. So what we're going to do is we're going to take the data, empty the data out of A2 and A3, we're going to take it out of the A2 and A3 register, and we're going to put it into an J and K operand register, or readout register. All right. So the data from A2 and A3 has moved into the J and K readout register, respectively, and that's clock period 2 of the instruction. Notice we still haven't done anything with them. All we did was we moved them out of the actual register. We emptied the register out. We took the data out of the register. Well, we didn't. Remember, it's a non-destructive read, so it's really still there. But we just moved a copy of it into the readout register.